Sure. Yeah.
Okay. Okay, so good afternoon, good morning, or good evening, wherever you are. It's my very great pleasure to welcome you to this latest Simons Institute talk. The speaker today is Tuomas Sandholm. Tuomas Sandholm is the Angel Jordan University Professor of Computer Science at Carnegie Mellon University, and he describes himself as a serial entrepreneur. His research focuses on the convergence of AI, economics, and operations research. And one of the many remarkable things about Tuomas is that he's made fundamental, lasting, and significant contributions in each of those areas. He's won a string of awards in recognition of his research. These include the Marvin Minsky Medal from IJCAI, the IJCAI Computers and Thought Award. He was the recipient of the inaugural ACM Autonomous Agents Research Award in 2001. He's a fellow of the ACM of AAAI and Informs, and he holds an honorary doctorate from the University of Zurich. He's an extremely prolific researcher and one whose research is always absolutely of the highest international standard. So Tuomas, it's my very great pleasure to be able to welcome you to give today's talk on finding and certifying near-optimal strategies in black box extensive form imperfect information games. The floor is yours.
Well, thank you very much for that very kind introduction. Can you hear me properly? Okay, so I'm going to start out by talking a little bit about the big picture of game solving and how that's really changed dramatically over the last 17 years or so. And then kind of my thinking about how to think about game solving. And then I'm going to jump to the specific technical topic. And that technical topic is finding and certifying near optimal strategies in optimal strategies in black box extensive form imperfect information games. And that part is joint work with my great PhD student, Brian Hu Zhang. Okay, so there has been amazing progress in game solving over the last 17 years. And a big part of this was work on computer poker in the AI community. The scalability, let's say, of imperfect information game solving has really jumped dozens of orders of magnitude over that time. So if you think about look at 95, say, at around 95, the biggest imperfect information game that had been solved had about 140,000 nodes in the game tree. And today, we have superhuman strategies for games that are of the size of 10 to the power of 165 nodes in the game tree. So you can see that there's been dramatic improvement. And I don't actually think about game solving anymore as like one algorithm, or here's an algorithm for solving a game. It's better than this thing or so on. And nowadays, I think of game solving as kind of different modules that address different aspects and get glued together into these different pipelines of game solving. And we are doing that in both my academic research group at Carnegie Mellon and at my startup company, Strategy Robot and Strategic Machine. Same kind of thinking, maybe a little bit different technologies. What are the modules? Well, one is automated abstraction. That's a key module. So how do we actually take the game and make some sort of a smaller game that's strategically identical or strategically similar, so that when we solve the abstract game, we can get good strategies for the original game? And there's really two different sides. It started from state abstraction algorithms, and so there's some sort of automated timing going on here. Let me just turn that off. Okay, that should be better. So state abstraction first, and then more recently action abstraction. And now both of those can be done with guarantees on solution quality. So you can guarantee that when you solve the abstract game, either you get an exact equilibrium in the original game or something within a bound of equilibrium where the bound depends on measurable aspects on the difference between the abstraction and the real world. Another module that's really important is real-time sub-game solving. It used to be that, of course, in perfect information games like chess or Go, you did real-time sub-game solving. These actually go back as ideas, at least to the 50s with Samuel's checkers program. And when we teach AI, we oftentimes talk about game solving like this, that there's some sort of search algorithm, there's a limited depth horizon, there's an evaluation function, and so on. But this was not doable for imperfect information games for several reasons. And only in the last few years, really the last 5 years or so, real-time sub-game solving has become possible in imperfect information games. And even more recently, depth-limited real-time sub-game solving. So the history went first, just solving the end game, typically in a finer-grained abstraction, and the whole game could be afforded to solve. And then more recently, mid-game solving. And so now you can actually do this in imperfect information games as well. Equilibrium finding algorithms, lots of work, of course, there. And that's probably where most of the work has gone into. And by the way, here I'm only showing work and modules from my lab, but on these modules, there's been a lot of work from other AI groups as well. And in those papers that I'm citing here, you can find all of those references. So equilibrium finding algorithms, there's really two main families nowadays. There's regret minimization algorithms based on counterfactual regret minimization, and real offline first order optimization methods. And the latter have a better worst case convergence rate, but the former just continue to be better. Both are improving by orders of magnitude, but the regret minimization based somehow continue to be a little bit better, which is actually a kind of a paradox that I want to continue to try to solve, as I have been for the last 10 years. Incorporating deep learning. Now you can actually incorporate deep learning for various purposes in these algorithms. And oftentimes you can actually have these algorithms that have guarantees, and then you just put a deep learning box in there, and that actually ruins the guarantees. But you can say that if the deep learning box does the right thing, then the whole thing still has the guarantees. So in a sort of way, it's a part of a guaranteed framework. Pruning. Of course, pruning, like alpha beta pruning, has been a classic in imperfect information game solving, but now you can do it in perfect information game solving, And now you can do it in imperfect information games as well. There, it's trickier because the values of the different parts of the game tree keep changing during the solve. So some of the pruned parts of the tree turn out to be actually not prunable after all. And you have to bring them back into play, and then you have to warm start their iterations with clever techniques as if you had never pruned them in the first place, and so on. Similarly, warm starting, these CFR-based techniques, it was believed that you can't warm start them, but if you do it in a really clever way, it's actually possible to warm start them. And that allows you to start from, for example, strategies that have been computed in coarser abstractions, or strategies that have been computed with some techniques that don't have guarantees, like reinforcement learning, or manual insights, manually made strategies, and so on. Automatically sparsified LP for equilibrium finding. So it used to be that LP was a state of the art for solving two-player zero-sum games until about 2004, where new techniques started coming through. But recently, LP has become again competitive by automatic sparsification of the LP first, and then computing equilibria by incorporating qualitative models. That's the idea that sometimes you have intuition about what the answer might look like. some sort of qualitative intuition of what strategies should look like. You can actually incorporate that now into some of these equilibrium finding algorithms, and that allows you to solve these problems faster. And it sometimes actually allows you to solve game classes that are not solvable without those qualitative insights. I don't mean just computationally, but there are no algorithms for those classes. Once you put the qualitative insights in, they start to fall into a different class for which algorithms exist. And the nice thing about that is that these qualitative insights, they can be guesses, and the guesses don't have to be right. So the solver will actually say, okay, well, your insights were wrong. There is no equilibrium that satisfies those qualitative insights. Algorithms for equilibrium refinements, lots of work on that, of course. And just to highlight one example, the main equilibrium refinement for extensive form imperfect information games is trembling hand equilibria. And those were wildly unsolvable until 3 years ago. You could solve games with maybe a handful of nodes. Now we can exactly solve games with around 30,000 sequences or so. So not to the same level as Nash for poker, but still to reasonably sized game models. Self-improvement techniques. This is actually kind of a nice new kind of way of including human insight in this. So you can, and this started from our work on Libratus, where one of the 3 modules was self-improvement. And it's not what you might think. You might think that it's trying to find weaknesses in the opponent and trying to tweak your strategy to exploit them. It's not that. It's looking at what are some actions that opponents have taken that have been outside of our abstraction, and looking at those as to how far were they from our abstraction, and then filling those into the abstraction and solving those parts of the game tree cleverly so the whole game still glues into an equilibrium. So you can actually refine the abstraction as you're using the tool based on what the adversaries have actually played. So that way, if the adversaries invent some completely new strategies, say that your algorithm didn't happen to consider in self-play, that will actually get fixed as you play against the adversary. Finding correlated and course-correlated equilibria, algorithms for multiplayer games. Again, multiplayer games, even in normal form, are extremely difficult, but we showed that by using these depth-limited search techniques, you can actually do superhuman play, for example, in multiplayer poker, no-limit Texas Hold'em with 6 players. And solving team games with pre-game correlation in the team, and opponent exploitation. This is the idea that you can look at how the opponent plays, either based on historical data or based on actually online data as you play them, and you can start to exploit the opponent's weaknesses. The downside with that is, by and large, that as you exploit the opponent, you become open to exploitation yourself. But we showed that that trade-off doesn't actually start at 0. So you can exploit more than any game theoretic strategy would and still be completely safe yourself. And we actually do a lot of hybrids where you start from a game theoretic strategy and then you can start tweaking your strategy in parts of the search space towards exploiting your opponent when you have a lot of data about the opponents in those parts. So as you can see now, there's lots of different modules here, and depending on the application area, you might want to glue them together. Which modules do you bring in, which algorithms within the modules, and so on. So it's no longer the case that, hey, here I have a new algorithm for solving a game. You might have a new algorithm for some module in these pipelines, and so on. Okay, so one of the issues, and now I'm starting to move towards the problem that I'm going to talk about today. One of the issues that we've seen a lot in my startup companies working on game solving is the question that the customers asked: what if the game model is inaccurate or unknown? So you're solving a game model and you're getting a good solutions to the model, but what if the model isn't reality? And how do you even know if the model is reality? And one kind of practical answer is sensitivity analysis. So change the model, tweak the model, and then resolve it. See if the answers are similar. If so, then you can be pretty sure that the recommendations are robust to changes in the model. Now, moving to the more theoretical side of that, I mentioned these lossy game abstraction techniques with epsilon exploitability guarantees. And this is something that I started with Satinder Singh on stochastic games, and then with my PhD student Christian Kröhr, we had this sequence of papers that extended that to real extensive form games. So we can actually guarantee that if you solve an abstraction and can prove that the abstraction, if the abstraction is close to the reality, the strategies that come out of the abstraction are close to optimal for the real game, not just for the model. So while this was motivated by computational speed and was looking at the gap between a game model and abstraction, it occurred to me that you can actually use the exact same theory to bound the gap between reality and the game model, the earlier gap there. Now, the third approach here, and this is what I'm going to talk about today, is the first techniques for computing provably optimal strategies, equilibrium strategies, or near equilibrium strategies, while searching only a tiny fraction of the game tree. And this was motivated by some thoughts that I had, kind of more like hopes I had as we were working at Strategy Robot. So I was looking at these huge games that were only given by simulator access, and it seemed at first that you'd have to try everything, try all possible strategies for player one and for player two and all pairs before you can actually guarantee anything. And then I started thinking that maybe that's not the case. Like if you're playing, let's say, some sort of a real-time strategy game, maybe if you've made a terrible mistake somewhere in the middle of the game, as an example, maybe you know that that was a bad action before playing down the rest of the path. Or if the opponent has made a terrible action, maybe you know it's terrible already right there and you don't have to play the rest of the game. So that gave me the hope that maybe we can actually compute actual equilibria in these games without actually searching the whole game. And turns out now that you can, and this is brand new work from just last year and this year. We give an algorithm with the optimal convergence of O tilde number of nodes divided by square root of t convergence in this setting. And this is very different from prior methods that can be exponential in the tree size. And by prior methods, there really haven't been too many. I'm going to mention two, MCCFR and another piece of work that I did with my student Gabriele Farina. But this is by and large a new area of trying to compute equilibria in these black box games that really are game theoretic equilibria in the full game, not just in the part of the model that you have actually generated. So black box games. Here, the game is not explicitly given in the form of rules, like maybe in poker, but rather it's accessible only by playing the game. So somebody gives you the, let's say, Xbox game, you get that for Christmas, and now you get to play in it and you get to learn to play. But nobody tells you the list of rules of some Xbox game. Here, the AI can control all players during the practice phase. So I don't, in the practice phase, have to play against an adversary. And in the practice phase, also I can make catastrophic mistakes to learn from the game and how to play the game. What are the rules and how to play it? And these catastrophes don't really cost me anything because I'm just practicing. I'm sitting on my couch playing Xbox by myself as the AI. So this is not a regret minimization setting in the sense that we don't care about the payoffs during the practice phase. We just want to have as strong a possible strategy by the end of the practice phase that can be used against any opponent. And this type of setting is actually quite common. It happens in war games, strategy video games, financial simulations, and so on. So here we have, for example, pictures of StarCraft 2 and Dota 2. And then we're doing quite a bit of work like this on real-world domains at Strategy Robot. Any questions on the setting? I want this to be super clear that what's a black box game. And I want it to be clear that we actually can control all of the players during the practice phase, and the rewards during the practice phase don't really cost us any real money. We're just using that practice phase to learn what the game is and try to learn how to play it well with guarantees. Any questions on that?
Can I ask a question?
Yes.
Hi. So do we have access to the reward system, and do we have access to what exact state the agents are in and what exact action they took?
Good. Yeah, I'm going to answer all of those in detail. Those are great questions, but let me just postpone it because that's coming up.
Okay.
Okay. All right, let me move on then. So how do we learn, or how does anybody learn to play black box games? And there's been really 3 approaches so far, 2 before this and this approach. So one, and maybe, well, not maybe, the most predominant approach has been deep reinforcement learning. And deep reinforcement learning is inherently a single agent technique and has guarantees only for the single agent setting. But it has found some practical amazing success in some of these real-time strategy games like Alpha Star playing StarCraft 2 or OpenAI 5 playing Dota 2. And those are pictures of that. So that's in great practical performance for a while. So for example, in both of those examples, AIs that have been generated with deep reinforcement learning, sometimes with prior human play knowledge to start out with, sometimes not, have reached levels where they can actually beat a world champion team. However, there's a major issue with those approaches, which is that they give no exploitability bounds. And if you think about what game theory really is, what's game theoretic equilibrium finding, this is what it really is. It tries to find strategies that have these exploitability guarantees, that no strategy can exploit me more than epsilon. And because it has no exploitability bounds, it's actually not just a theoretical problem, it leads to strategies that can be beaten in practice also. So for example, in Dota 2, after they had beaten the world champion team, after a few weeks, even average players were able to beat the AI once they had found the weaknesses in the strategy. So again, no exploitability bounds, and it manifests in practice as well, in that even average players can beat it. Another approach, this joint work with my student Gabriele Farina, is bandit regret minimization. It's different than what I'm going to talk about today in that it's really minimizing regret along the way. There's no free practice phase. And also we're not controlling both players there. We're controlling just one player and it needs to learn the game against anybody. And bandit, that's important here in that we're only getting feedback on the actions that we actually took on the game. We're not getting feedback on the actions that we didn't take. Like most traditional equilibrium finding algorithms for this space, they are not bandit. They assume that you get feedback on all of the actions, not just actions on that you took. This converges to epsilon equilibrium after a number of samples in the game that's polynomial in n, the size of the game, counted as the number of nodes, and 1 over epsilon, where epsilon is the epsilon guarantee on exploitability. And what's a sample in this talk? A sample in this talk is one playthrough in the game. So from the root to the leaf, that is a sample. It's not the full traversal of the game tree, and it's not just one action. Again, a sample is a playthrough. Issues here with this approach, and also online MCCFR has these issues and also other issues. The worst case exploitability bounds are trivial until the number of iterations is much larger than n. And you need to expand the rest of the game tree to compute ex-post exploitability guarantees. So there's two ways to get guarantees in game solving, really. One is the worst case exploitability bounds that say that for any game, this algorithm is going to find an epsilon that's at most this big. But here, these worst case bounds are trivial until the number of iterations that you've run the algorithm is much larger than the game. And the other approach is that you can just try to run an algorithm, and then you check at the end how bad is the exploitability by doing a best response computation. And to do a best response computation, you need to expand the rest of the game tree here. So you have basically no hope, unless you have some additional structure maybe, of finding an ex-post guarantee without actually revisiting the entire game tree, which is way too big in all of these examples. Okay, so now let me move to certificates, which is the approach in this talk. Here we want to compute the Nash equilibrium of the game, or an epsilon Nash equilibrium, by incrementally expanding the game tree. And we can compute exploitability bounds ex post without ever expanding the remainder of the tree. So we're going to only expand part of the game tree, and then we get both these worst case game independent bounds, and we can also come up with these game specific and strategy specific ex post exploitability guarantees without actually expanding the whole game tree. Okay, so now coming to your question, Anna, now we're going to start to talk about what this looks like. And here's a very small example. We're going to talk about experiments that have millions of nodes in the game trees, even infinite game trees, and so on. But I want to show you a small example here, just to make it clear. So here we have, in this example, two players, player one and player two, and chance. So this is a standard extensive form game representation. If it's a zero-sum game, which we assume for part of this talk, then you have just player one's payoffs shown in the leaves, and player two's payoff is just one minus that. If we have a general sum game, then you would have at the leaf a vector of payoffs, one payoff for every player. And in this example, player one could go left and right, and if player one goes left, then player two could go left or right. If player one goes right, then chance plays 50-50 left or right, and then player two gets to go left or right. And that dotted line there is an information set that represents imperfect information. It says that player two at that information set doesn't know what chance did. So player doesn't know whether he's in the left of those nodes or the right of those nodes. All right, so that's an extensive form game, and that's exactly the representation that we work on. Nothing new yet. Now let me introduce two new notions, a pseudo game and a certificate. A pseudo game is a game without known utilities on all terminal nodes. So for example, I could say, I haven't really expanded the game tree fully, but somehow I know that at that left node, the payoff for player one is non-positive. So that would be an example of a pseudo game. It's a partially expanded game tree. In zero-sum land, this gives rise to actually two different games. A lower bound game in which the rewards are optimized for player two. So in this game here, we would assume that player one's payoff at that left node is minus infinity. And an upper bound game in which the rewards are optimistic for player one. And here we would assume that that node's payoff would be 0. Any questions on that? Okay. We call that a pseudo-terminal node because it's a terminal node of our pseudo game, but it is not a terminal node of the real game. Okay, so an approximate Nash equilibrium in a pseudo game is a strategy profile in which every player is probably playing an approximate best response, irrespective of what happens at pseudo-terminal nodes. So let's do an example. So here the green numbers show a strategy profile. So player 1 goes left with 0, probability right with 1, chance plays as before, and player 2 randomizes 50-50 between going left and right. You can convince yourself that this is actually an exact Nash equilibrium of the game. Why? Well, if player 1 moves right, then player 2 can do no better than 0 expected utility, and he can get that with playing half-half. And if player 2 plays half-half, player 1 is going to get 0 by moving right, and at most 0 by moving left. So player 1 might as well move right. So this is not even an approximate Nash equilibrium here. This is an exact Nash equilibrium here. And furthermore, it's an exact Nash equilibrium of the real full game, not just of the pseudo game. So we didn't need to expand the whole full game here to be able to determine what the Nash equilibrium of the real game is. And this is kind of the main insight of the paper. And now there's a lot of technical stuff that I'm going to go into in the rest of the talk. But if you want to remember one bit, this is the one bit. This is the idea. So this results in a Nash equilibrium regardless of what the pseudo-terminal node hides. And what's a certificate here? A certificate, it's a pseudo game created from partial expansion of the full game plus a Nash equilibrium of that pseudo game. So we need to have the strategies and we need to have the pseudo game that proves that the strategies are indeed Nash equilibrium or approximate Nash. So we're certifying that the Nash equilibrium is indeed a Nash equilibrium by having this partially expanded game tree, which we call a pseudo game. Okay, now we can ask, okay, yeah, you just made up an example where you didn't have to expand the whole game tree. How well does this work in practice? When does it lead to small certificates? Or is it the case that in most games you pretty much have to expand the whole game tree anyway?
So may I ask a question, please?
Yes.
How do you certify that the values that you have on the pseudo games are correct? So I understand that you give the strategy.
You mean like this red now? Can you see my cursor?
Yes.
You mean how do we guarantee that this bound here, this red bound is correct?
Yes.
Oh, that is a given. Those are inputs to the algorithm. These come from the simulator, and I'm going to talk about how much sampling you need to do and how do you do the sampling and things like that in the rest of the talk. But these are coming from the simulator. And if they don't come from the simulator, if the simulator says, I don't know, then the bounds can be minus infinity and infinity. And it's still, the whole thing still works. You don't have to have finite bounds on everything. Well, of course, the tighter the bounds that the simulator can give you, the smaller the certificate that's needed. Okay, so when do small certificates exist? When do small certificates exist? And specifically, what do we mean by small here? We're saying certificates of size order n to the c and times polynomial in 1 over epsilon. For some c less than 1. N is the size of the game tree in nodes, so we don't want to have to expand the whole game tree. This is just saying that, you know, we want to expand less than the whole game tree. When can we do that? Okay. I'm going to give you many answers. I'm going to start with 2 very intuitive settings where I can explain quickly that there's always short certificates. And then I'm going to move to the real imperfect information extensive form, where it really depends on the game. But one answer is that they always exist in perfect information, zero-sum games with no nature randomness. And why is that? Oh, by the way, minor caveat here, under reasonable assumptions of the game tree. So there are certain weird game trees that you could construct where it's not quite the case, but under reasonable assumptions about the game tree. For example, a roughly uniform branching factor and depth and alternating moves. The proof is very simple. It actually heavily relies on something that's already known, which is that the optimal alpha beta search tree is a certificate. And in particular, from old results by Knuth, the size of the certificate is roughly square root of n. So in perfect information games, you can actually get away with a certificate of size square root of n. Another example is that they exist in normal form games. So normal form games are matrix form games. And here again, small caveat there, they have to be square-ish. So not something that has a huge number of strategies for one player and almost nothing for the other. So here's an example. So the column player gets to pick some strategy between A and G, and the role player between T and Z. That's a normal form game. And how do we know that that has small certificates? Well, there's a result by Lipton et al. From 2003 that says that there's an epsilon Nash equilibrium where each player mixes between only log m divided by epsilon squared pure strategies, where m is the number of strategies for a player. So what that results, Lipton's result says that, okay, there's some small support for the column player and some small support for the row player, such that the mixed strategy played on only those supports is an epsilon equilibrium. Okay, so now how do we convert that into a certificate? That's not quite enough. So what we can do for a certificate, we only need those rows and columns, but we also need all of the other cells for those rows for the column player and all of the other cells for those columns for the row player, because we want to make sure that the opponent can't switch to something else and significantly exploit us. So that's why we get an extra factor of m here. And this shows that you get an order m log m divided by epsilon squared size certificate. So again, very small certificate suffices. So small certificate exists in games where the players have perfect information or no information. The normal form case is the no information game. But what about in between? A lot of these imperfect information games are in between perfect information and no information. What happens there? And that's what I'm going to talk about in the rest of this talk.
Can I ask a question?
Yes.
So I think it's probably related to the previous question. So it's what's confusing is that you don't know you don't know how to find these certificates. So how can you exploit this to solve the games faster?
Oh yes, I haven't given you any algorithms yet. So far, it's all about existence. I'm going to give you many algorithms later in this talk.
Okay. Okay, sure. So I'll wait. Yeah, thanks.
No, that's good. You're jumping ahead, and that shows that you're on the ball. That's great. So unfortunately, small certificates don't always exist. Here's an example. Consider this game where you have matching pennies, where one of the players tries to, you can either choose heads or tails, and the other guy can choose heads or tails. One player wants them to be the same. The other player wants them to be different. That's matching pennies. Here we're going to repeat the matching pennies t times, each round worth 1/t points. After each round, player 2 learns what player 1 played, but player 1 doesn't learn anything. So player 1 doesn't observe anything. This is our counterexample game. And the game tree size here is 4 to the power of t, because at every round, each player has 2 choices. So at every round, there are 2 times 2 is 4 choices total. And there's t rounds. Now, the theorem is that any epsilon certificate of this game must have size omega 4 to the t times 1 minus order epsilon. So you need to basically have the whole game tree expanded before you can certify Nash equilibrium in this case. This is, of course, highly tweaked, a manual bad case. The proof sketch is just that player 1's strategy must have high entropy, but this is not possible unless lots of nodes get expanded. Now, continuing with bad news, computational hardness. It's NP hard to approximate the smallest certificate of an extensive form zero-sum game to better than order log n multiplicative factor. The proof idea here is just a reduction from set cover. One guy tries to, in a certain game, tries to just cover all of the other players' options. Now, let's start to talk about a little bit more detail of the simulator, what kind of access we want. And I'm going to start from our first paper on this, which was the NeurIPS 20 paper. And then I'm going to relax what we need to talk about some of the work in the AAAI 21 paper. So we're going to assume access to a simulator. This is the black box that our game learner is accessing. So think about Xbox. You just got some Xbox game for Christmas, and that's your simulator. We can play the game, or the AI can play the game from the perspective of all players at once. So the AI can know what each one of the players observes in the game, and the player can control what each one of the players does in the game. But of course, the game tree is so huge that even with that control, you can't play through all of the paths. The simulator gives bounds, which don't have to be tight, on future utilities. Like, let's say that I've lost a huge asset by making a big mistake. I know that, okay, I can't get the maximum payoff of the game because I've already lost this huge asset that was very valuable. The simulator also allows us to control nature actions here. And this is the thing that I'm going to relax later in this talk, but I want to start simple. So, and what this allows me to do, it allows me to take the game into any state from the root and then continue playing it from there. So in other words, I get to jump around in the game tree as much as I want. In the second part of the talk, I'm going to remove that and say that I can only start from the root of the game, and Xbox is going to take me wherever Xbox wants to take me, and I cannot control the path nature nodes. The goal is to compute and verify an exposed approximate equilibrium with only this black box access. And exposed means that it can be game specific and it can be strategy specific. So I'm going to have this learning phase, and at the end of the learning phase, I can do an extra step of computation that I want, and then somehow compute how good my strategy is. And then that strategy has to be good against any future opponent. So when we measure how good the strategy is in exploitability, we do it in the normal game theoretic sense of finding the toughest opponent. In other words, the best response to our strategy. We're going to output both an equilibrium strategy and the bound epsilon, the exposed bound epsilon that we compute. More bad news. With only black box simulation of an expensive form, even zero-sum game. There's no equilibrium finding algorithm that runs in time polynomial in the size of the smallest certificate. Somehow not that surprising, because you could actually generate games that have very small certificates, but they might be hard to find. And the proof is a one-player SAT game. The certificate is of size, the smallest certificate is of the size order log n, but there's no sublinear time. It's basically trying to find a satisfying assignment to the variables. Now we're going to do it anyway. Yes, this shows that there are bad cases, but we're going to now generate an algorithm to do it anyway, and then we're going to see how fast it is in practice, in runtime and in terms of a number of samples it needs. So what we're going to do here, we're going to repeat until satisfied. You can put in your favorite stopping criteria there. We're going to solve both the upper bound and lower bound pseudo games exactly. For example, using an LP solver in the sequence form. We're going to create the next pseudo game by expanding all pseudo terminal nodes in the support of the optimistic profile, in which the max player plays her equilibrium strategy in the upper bound game and the min player plays her strategy in the lower bound game. So this is in some sense a game theoretic interpretation of this classical mantra of optimism under uncertainty for exploration. And then we're going to output the pessimistic profile, and epsilon, which is the difference in values between the upper and lower bound pseudo games in the pessimistic profile. So when we give the guarantees, we have to be pessimistic, but when we're doing the exploration as to what to expand next, we're optimistic. And the intuition is that if you want to hang your hat on something, in the perfect information setting with no nature randomness, this is just alpha beta search. But this is more general because it applies to imperfect information games. The theorem here is that the expansion in the second step expands a node if and only if the game is not already solved. So in that sense, it's not doing any unnecessary work. And therefore, if you run this long enough, it will find a Nash equilibrium. This works even on games that have unbounded rewards. So let me show some experiments here. The first is a search game, which is a standard benchmark in the field. It has about 200,000 nodes, 11,000 information sets, and we see that the size of the certificate this finds is about 5 or 6% of the size of the game. Then in a Glufspiel, which is a standard benchmark, we actually make 3 variants of Glufspiel. One is the perfect information variant, then there's a real Glufspiel, and then there's a Glufspiel where the cards come in random order instead of sorted order. And we can control the size of the game by how many different ranks there are in Glufspiel. So here we're going from 4 rank to 6 rank. We're going from games with about 2,000 nodes to games to about 9 million nodes. And what do we see here? Well, in all of the cases, it works. And the bigger the game, the smaller the fraction of the size of the certificate. So that's good. We see that in the perfect information variant, we get to very small fractions like 1% or even 0.5% already at this size. In these imperfect information games, the certificates are relatively larger. We're looking at like 10% or 20%. But again, the bigger the game, the smaller the percentage. So this becomes more powerful in the bigger games. And then in Leduc poker, and we can vary the number of ranks to vary the size, the game tree is actually infinite because we allow an infinite number of re-raises in this variant. So these are infinite games, but we can still solve them with and get relatively small certificates. Okay, now I'm going to move to more realistic simulators. This is what we had before. The simulator allows us to play through the game from the perspective of both players. It gives bounds, and allows us to control nature nodes. Now I'm going to take this one away. We can no longer control the nature nodes. Instead, we have to always start by playing from the root, and the game is just taking its own nature actions, and we're controlling only the player actions. Okay, so now we can't really ever be sure about the probabilities of the nature actions at a nature node, because if we get unlucky, there are some actions that nature never gives us, or they're so low probability that we didn't see them in the training phase, but we might see them in actual play later, and they might be catastrophic. So we can't get guarantees for sure. So here we want probabilistic guarantees, and we want to say correctness with high probability, say 1 minus t to the minus gamma for some gamma greater than 0 after t iterations. Now, here's a roadmap for the rest of the talk. This splits based on what happens at a chance node. In our NeurIPS 20 paper, we looked at the case where when we visit a chance node, it gives the full distribution at that node. What are all of the actions that chance could take and their probabilities. Now we're going to talk about a chance nodes where we don't get all of the actions and we don't get their probabilities. We just get one sample from the probability distribution of the chance node that we visit. Here, if we're in the sampling limited case where the simulator is very slow, like we see in a lot of our real world cases where one playthrough takes over a half an hour. So clearly in those settings, we're sampling limited, and that's very different at, let's say, Dota 2 or StarCraft 2, which AIs can play against each other very quickly. There, when it's sampling limited, I'm going to show you an algorithm that uses an LP, because we can afford to solve the LP exactly and therefore do the reasoning very well in order to minimize the number of samples. When, on the other hand, we're in a compute limited setting where the equilibrium finding reasoning is a bottleneck and accessing the simulator is fast, that's more like the StarCraft type of setting, or poker if you like to play poker as a black box game. There, we're going to have a new algorithm that uses regret minimization as part of it. And that is usable even in general sum games, not just zero sum. And in those cases, it computes course correlated equilibrium instead of Nash, as regret minimizers usually do, but never in this setting before, this black box setting. Okay, so the lower bound for this setting, consider any algorithm with the following guarantee. For some constant gamma greater than 0, given a zero-sum game in our black box setting, with t game samples, again, each sample is a playthrough, the algorithm outputs a pair of strategies xy and a bound epsilon t, such that with probability 1 minus order t to the minus gamma, xy is an epsilon Nash equilibrium. Then the lower bound is like this. The epsilon is omega of square root of log t over t. And our goal, by the way, we proved this in the paper, our goal is to match this bound with actual algorithms. The main tool is pseudo games as confidence bounds here. At nodes that we have not yet expanded, we use bounds given by the simulator, as before. And at nature nodes, H, we give each player a made-up reward that's bounded by from minus rho to rho, where rho is computed as follows. So first, there's the delta factor, which is the range of utilities that are possible from that node H onward. And then there's this other factor, which is square root of 1 over 2 th, where th is the number of times that h has been reached so far, times log 1 over epsilon, 1 over delta, where delta is the confidence parameter. Remember, we wanted to have. So the intuition here is that rho represents the uncertainty in the nature distribution at the node nature node H. The intuition, well, if you're familiar with UCP, upper confidence bounds, this looks a lot like that, but not exactly. And this is not a coincidence, as I'll discuss later. The choice of confidence bound, well, so far what I showed you on the previous slide is this. During the equilibrium computation, the values of the children are changing, so we need to use a Höfting bound to be robust for rho. And that's what we did. Now, here's a new idea that we had since the AAAI 21 paper. During the best response computation at the end, after the equilibrium finding, the strategy profile after H, below H in the tree, is fixed by induction because we have already fixed the opponent strategy. The nature strategies are fixed by definition, and we have already fixed our own strategy below that point because we're computing the best response bottom up by induction. So during the best response, the strategy profiles after H are fixed, so where you can use a tighter empirical Bernstein bound. This is a formula from Maurer and Pontil in a different context. It doesn't matter that much, but here S is the unbiased sample standard deviation, and delta prime is the range of possible utilities from H under the fixed strategy profile, which may be much smaller than the original delta. Okay, so we can actually use a different confidence bound technique during the equilibrium finding and a tighter one in the best response computation. So we can get an even tighter best response bound epsilon for those same strategies that we're computing using that rho technique, the original rho technique. By the way, that's so new that we haven't yet implemented that. So in the experiments I'm going to show you, we're not using that yet. We're just using the former technique for rho. So the new results will be even better, but I just don't know yet how much better. Okay, now pseudo games as confidence bounds. Here's the theorem that this is correct, that the way of doing those rows is correct. For an appropriate choice of delta, with high probability at every time, for every strategy profile, for every player, the true reward of the player is bounded by the pessimistic and optimistic rewards achieved in the confidence bound pseudo game. In other words, the confidence bounds are actually bounds. And now to the algorithms. I'm going to start from the LP-based algorithm. We're going to repeat T times, solve both the upper bound pseudo game and lower bound pseudo game exactly, for example, using an LP solver in the sequence form. Then we're going to sample one playthrough from the optimistic profile again, in which the max player again plays our equilibrium strategy in the upper bound game, and the min player plays her strategy in the lower bound game. So this is again optimism under uncertainty for the sampling. And then we're going to create the next pseudo game. We expand all of the encountered nodes during that sample. And we're going to update the empirical nature distributions of nature nodes sampled during that play. The output is the pessimistic profile again, and epsilon t is the difference in values again between the upper and lower bound pseudo games. The intuition again is that in the perfect information setting with no nature randomness, it's still just alpha beta search. And in the one player multi-armed bandit setting, it's UCB. Well, not exactly, in that the algorithm has a different constant in the upper bound confidence bound term and a different constant in the regret bound, but essentially specialized to the multi-armed bandit setting with just one player, it is UCB. Okay, so the advantage of that, it's very sample efficient. The disadvantage is that the iterations are expensive because they require game resolve with exact LP on each iteration. We do warm start from the previous LP, whose values typically change very little based on the one new playthrough. So you get a good warm start, and that helps actually a huge amount. But still, you're solving an exact LP. And here's the guarantee. The best iterate of the algorithm converges at the rate of where the expectation over t is order nt times log t over t. And nt is the size of the certificate here, not the size of the whole game. And that's important because, as we showed, the size of the certificate can be much, much smaller, orders of magnitude smaller than the total number of nodes in the game. So now we're really looking at complexity as a function of the size of the certificate here, not as a function of the whole game. And that's what you want. And this is very different than how people are typically looking at equilibrium finding. Typically, it's always as a function of the size of the game. Okay, now, when you're in a setting where you're not so much sample bound, but you compute bound, you don't want to solve the exact LP every time you do a sample. So that's why we have this regret-based algorithm for that setting. And the idea is just use a regret minimizer like CFR for each player. What we do, we again repeat t times. We query the regret minimizers for all players to obtain a strategy profile. Then we sample one playthrough from that strategy profile. We pass each player's regret minimizer that player's optimistic reward. Create the next pseudo game by expanding all of the encountered nodes again and by updating the empirical nature distributions of nature nodes sampled during play. And we output the average strategy profile, as typically in CFR. Now, this has several problems. One, the strategy space of each player is changing over time. So you're not actually solving the same game, you're actually solving a different game at every iteration. This is okay. CFR handles this naturally. We actually, in the paper, we formalize what's required in terms of extendable regret minimizers. In the interest of time, I'm not going to go into that, but suffice it to say that CFR is one extendable regret minimizer. Some regret minimizers are not extendable. Problem two, we don't want to run a full CFR iterate on every sample. That's expensive. So what we do, we use Monte Carlo CFR plus outcome sampling, which is a standard technique, and nothing breaks then. And then the third question or problem is, what equilibrium gap bound can we now get, given that we're not solving the LP exactly? And that's what I'm going to talk about now. The natural game-specific equilibrium gap bound, which is what we used in the LP-based algorithm, again, which was the difference in optimistic best response value using the final pseudo game, doesn't converge as O tilde 1 over epsilon squared in the worst case. There are these pesky cases where you have these low probability actions that we talked about. But we know that the worst case over games equilibrium gap bound of the algorithm does converge as O tilde 1 over square root of t for the same reason that MCCFR does. So what we can do in practice, we just take the former. It's basically always smaller in practice. In theory, you could compute both bounds and take the minimum of the two. So that's how you get the best of both worlds. All right, let me finish with some experiments. And now these are experiments with this new algorithm, that uses a more realistic access where you just get one sample of a nature node when you get to a nature node. So the nature node doesn't tell you all of the actions that are available, or that doesn't tell you all of the probabilities on all of the actions. And these are pretty dense. So let me now walk through kind of what's what. On the x-axis, we have iterations on a log scale. Each iteration is one sample followed by that computation. And one sample is one playthrough. And on the y-axis, we have the Nash gap on a log scale. So lower is better. We have this horizontal line is a range of players' reward in the full game. So if we're above that, we have really no guarantee on the gap. We're trivial. Below that line, we're non-trivial. And then the vertical line here is a number of nodes in the full game. So as long as we're on the left side of that line, we have not yet expanded the whole game, so we're getting some benefit. And what we see here, let's look at the solid lines. These are the certificate LP algorithm and the certificate MCCFR algorithm that I talked to you about. And we see that they are non-trivial. We are getting benefit. And we can also see what are the actual exploitabilities with those, the dotted blue and green lines. And they're, as you would expect, better than the worst case bounds. We also ran MCCFR as a benchmark, and it's kind of an unfair benchmark in that it doesn't give you any guarantees. But because we know the game, we can actually compute an ex post guarantee ourselves for using the whole game. So that's MCCFR, how well it performs on that game. So here it's the best, here it's not quite the best. But again, it cannot give you guarantees without expanding the whole game tree. So it's not really an actual competitor, more like a theoretical benchmark here in this case. Okay. On the figure here on the bottom, same x-axis, certificate size on the y-axis. And we see that, yes, the certificate size is much less than the number of full nodes in the game tree as you would want. So in all of the games with all algorithms, we find non-trivial certificates without expanding the full game, and in fact with fewer game samples than there are game tree nodes. MCCFR converges quickly in reality, but doesn't give you bounds. So it's more like a theoretical benchmark, and we see that getting these theoretical guarantees only costs us about a factor of 5. So we need to do 5 times more samples, but with that we can actually get guarantees. And as you would expect, the LB-based certificate finding has better sample efficiency and final certificate size than the regret-based, because it was geared towards sample efficiency, while the regret-based was geared more towards computational efficiency. So depending on whether you're sample bound or compute bound, you might want to choose one or the other. Okay, so let me conclude. Very short conclusion: black box imperfect information games of at least moderate size now can be solved for the first time. In other words, we can get the non-exploitability guarantees of game theory even in these settings where we don't know what the game is. And here are some the 2 papers on this. And then in addition, we talked about the new concentration result for which we don't have experiments yet. Okay, let's take any further questions you may have.
Okay, thanks, Tuomas. Questions, anybody? Rupak.
Thank you for this really fascinating talk. I'm coming from a somewhat different area where we're trying to look at, control design problems in dynamical systems. Now, if you look at your setting of these black box games where you can simulate the system dynamics also in the presence of certain environment disturbances, how many of your computational results do you think would transfer to a setting where essentially we are trying to find winning strategies in these kind of dynamical system games, right? So I want to find a robust controller against some environment noise. I can simulate the system, any number of times. Can I use your algorithms in this setting as well? Or is there something specific to the games that you're looking at that makes these algorithms better?
So I don't think there's anything specific in these games. If you're talking about the benchmark selection here, we try to come up, you use kind of standard benchmarks from a host of different domains. There's different types of card games. There's poker, there's Goofspiel, which is a trick-taking game instead. There's the search game, which is kind of a structured graph-based security game. And then there were the
But you
infinite
see, my
games.
question is, if I were to take your algorithms and apply them, let us say, to robot control, which often is this kind of a two-player game between the controller and the disturbance in some kind of imperfect information setting. I don't see any reason why they would not transfer, right? So it's...
I don't either. Well, let me say one where I would look for, I don't know that there's a problem, but in transferring them, but where I would look for that. One is that here we're assuming that the branches are discrete. So the actions are discrete, they're not continuous. But maybe you could discretize the action space.
Discretizing the action.
And you might take some loss there. We actually have a paper with Christian Kröhr that looks at the loss that you get in game theoretic settings from discretization and how should you do the discretization to minimize it. A uniform discretization is not best, but so you could look at that. So there are better ways to do discretization than uniform. But so that's one where maybe in some theoretical way this could go astray, but I don't think so. I think it should be good.
Oh, thank you very much.
Okay, other questions? Well, while we're waiting to see if there are any other questions, let me just ask. So, I mean, this is very much focused on I mean, your work over the last few years has been very focused on kind of games like poker and so on. I mean, other applications beyond game playing? I mean, what realistically might it be used for ultimately?
Oh yeah, that's a great question, and I actually believe so much in this that there are real applications that I found in two companies, Strategy Robot and Strategic Machine, to actually feel these in real applications. We are actually doing real applications. I can't really say which applications we're doing, but the press has gotten some wind of it. So if you wanna poke around what the press has said, you know, that's something. If you want to search on the Strategy Robot, the Strategic Machine, you can see what the press has said. I think that, you know, lots of different military games. There are a lot of zero-sum games in defense, security games of different kinds, and I don't mean just like Stackelberg, One Shot, that type of security game, but like security in the kind of broad sense of the word. There's I can give you the whole list of vision things that I think.
Okay, that's great.
Imperfect information auctions, that don't have dominant strategies. And one example, by the way, is the FCC incentive auction. The auction mechanism that was used for that is not a dominant strategy mechanism. So each bidder's best strategy depends on the other bidder's strategies, and nobody knows even one rational bidding strategy. And yet they reverse auctioned almost $100 billion, I think. In any case, tens of billions of dollars of spectrum with that type of mechanism where nobody knows how to bid rationally. So it would be nice, wouldn't it be nice if we could be rationally in that? Yeah. Negotiation, bargaining, political campaigns where it's like, okay, how much I should spend on different things and in different areas depends on how much my opponent does and how they exactly allocate. Product portfolio optimization, that's basically done as a single agent optimization today, assuming that the competitors don't have a competitive response, which is of course wrong. Pricing, same thing. Today it's optimized as a single agent optimization, assuming that others don't change their prices, which couldn't be further from the truth, and so on.
Okay, very cool. Okay, any other questions? Seeing anything come in? Oh, it's a question from Senthil Rajasakaran. Hello, Senthil. Nice to see you again virtually. It seems like different techniques would be needed to lift these techniques to more than 2-player games. Is this something you're interested in or have looked at already? For example, DOTA, actually, I don't know what that stands for, which has 10 players.
Oh, okay. So let me start from the last part of the question. It is not true. So Dota 2 is a 2-player zero-sum game. Yes, each player is played by a team typically of 5 players, but it's still a 2-player zero-sum game. So that's not a multiplayer game per se. And same with StarCraft, that's a 2-player zero-sum game. So I think that these techniques, except for the scalability question, these would apply directly to Dota 2 or StarCraft 2. Now, I am not saying that these certificates are going to be small enough for those games. That I don't know. And that's, I think, an interesting question, because that's how, when we would really be able to say where really is the boundary of what game theoretic techniques with guarantees can do. For what size of game can you give guarantees? I believe that there's always going to be a size of the game that's too big, that you cannot give game theoretic guarantees. And then you work on some unguaranteed techniques like deep reinforcement learning. But where is that boundary? I don't know. With these techniques, certainly now that at least the field is open, and we know at least it's working to an extent on these reasonably sized games of millions of nodes in the game trees. And we're not even pushing the scalability boundary with millions. It certainly goes way beyond that, but I'm not saying that this can solve Dota 2 or StarCraft 2. We're actually ongoing thinking that we're doing in the lab of additional structure. If you have some additional structure about the game, certain independencies and other things, you can actually solve much bigger games if you know that the games have those structures, even if you don't know exactly what the game is. Like one of my favorite examples is like, if you have let's say some real-time strategy game that has a little gremlin that's biting at your ankles and pestering you, it is not going to turn into a nuclear weapon that's going to explode everything at the end. It's going to always be that gremlin, and maybe it's going to get a little worse or a little better, whatever, but it's not going to completely change. And otherwise the game wouldn't be interesting if some of the gremlins mysteriously turn into a nuclear weapon in the game. So there's something about games that have this type of consistency that humans like and can understand, that already puts restrictions on what the game strategy space can be. And if we can somehow characterize as to what are those restrictions that would be helpful for bounding what the unknown pieces of the game might be in terms of bounds and so on, that would probably really increase the scalability of these guaranteed approaches.
Very good. Sentil says, I thought DOTA had 4 teams, but I don't know much about it, honestly, but thank you for the answer and the interesting talk.
Okay, well, if that's maybe there's some sort of a DOTA that has 4 teams. I don't know about it. The DOTA stuff that I know about is 2 teams of 5 players each.
Any other questions? I'm not seeing any hands up, and I'm not seeing any other questions come in the chat. Rupak has another question.
Just a quick follow-up to that. I mean, if you're modeling a 5-player game as the 5 versus 5 as a zero-sum 2 coalition game, you're kind of making an assumption that these 5 players have all the same knowledge, that they're correlated in their strategies. But this may not.
That's right. They do. They do. In Dota 2, if you put an AI to play it, you can have the AI look at all of the input from all of the 5.
Okay.
But you're right. I mean, we're also looking at kind of coalitional games for other settings where you cannot coordinate during the play, but you can coordinate before the game. So I can actually coordinate my strategies in advance, but I can't coordinate my information during play. That's also a very interesting setting, and we have other papers on that, but that's not what this pair of papers addresses.
Thank you.
Okay, any other questions? No, okay. I think then we've come to an end. So on behalf of everybody, thank you very much, Tuomas, for giving a typically energetic and thought-provoking talk. It's great to see your latest work, and it's going to be fascinating to see how that work unfolds in the next few years. I think you could, what I love about this is it's not all just deep learning, right? That's not the only game in town. I think that's what the message that I'm going to take home from this, which is a great message to take home. So thanks everybody for joining us, and tune in for the next talk. The details you'll find on the Simons Institute website. Thanks again, Tuomas.
Thanks a lot. It's great fun.